Hi everyone, welcome to lecture 4 of the nuclear physics series. Today we're going to talk about observables and how we can calculate them. And first I'm going to start with a brief overview of the potential method, which was developed by QCD. And this is an alternative to the Lucier method. It has various pros and cons, which I'll talk about at the end, but basically you can use it to get information about scattering phase shifts, binding energies, etc., just like you do for Lucier. So what we're going to do is create the following correlation function. We put down an operator for two nucleons at the source t equals 0. We go to a later time and put down an operator for the two nucleons separated by some distance r. And we calculate this for all possible r's on the lattice. And so we go to large Euclidean time, as usual, where we can pick off a single state. And we're going to get an overlap for the operator at the source onto the ground state. We get the exponential with time. And then we get an overlap of our operator at the sink, which has the two nucleons displaced by a distance r onto the ground state. And again, we have this for all possible positions r. And I want to just note at this point that this two-nucleon correlation function is exactly the same thing that we would calculate for extracting energies in the Lucier formalism. So remember there we had some position space operator, and then at the sink we had our two nucleons with some relative momentum. So we projected onto some momentum that we were interested in. And that's just the Fourier transform of this CNN as a function of r. And so the input at this point is exactly the same. So what's different is instead of extracting energies, we're going to take this psi naught of r and interpret that as a Nambu beta Salpeter wave function, which we can then plug into the Schrodinger equation to determine the potential. So here's the Schrodinger equation, just rearranged a bit. We have the momentum of the two-particle system squared over twice the reduced mass of that system. And then h naught is just grad squared over 2 mu. And then our potential is here on the right-hand side, and this is the thing we would like to extract. So in general, this is a complicated integral equation, and we can't get our potential as a function of both of the positions of both nucleons. And so we have to make an approximation. So what's done is a derivative expansion of this potential. And so to leading order, which has no derivatives, you get the central potential, which is a function of only the relative distance between the two nucleons times some delta function. And then there are higher orders that are neglected. So when I say higher order in what? I've written this as an expansion of the gradient over some scale lambda, and this is often called a velocity expansion. And in principle, if there was some velocity scale lambda that's much bigger than the size of the fluctuations of the potential that we're leaving off, then this would be a well-defined expansion. However, we don't have such a scale. It's not known whether these higher order terms are in fact smaller than the leading order term, which is the part that we keep. So this has to be checked. You have to look for some measure of convergence of this expansion from your data. Okay, so once this is done though, we can plug this in to the Schrodinger equation. The delta function gets rid of the integral, and so this becomes easy to solve. You can replace psi naught of r with the CNN of RT because everything else that was in this correlation function was independent of r, so those are just constants. And so what you get is a term that depends on the interactions that you can calculate from this two-particle correlation function. And it goes like the gradient squared of that correlation function divided by the correlation function itself. So This is just an alternate method for getting information of the two-nucleon system. As it stands, it doesn't help us much in terms of this exponential signal-to-noise problem that we have for two nucleons, because we still have to go out to very late times where only a single state contributes. So the real benefit comes from looking at the time-dependent version of the Hell potential. So if we go back and we look at the form of this correlation function, so here we assumed that only a single state, the ground state, contributed. If, however, we don't go all the way out in time, we just go to some intermediate time where there is still contamination from excited states, we know that that contamination from excited states is just going to look like some additional time dependence on top of the exponential of the ground state energy that we would see if we were at single state saturation. And so we can interpret that extra time dependence coming from excited state contamination as just being a time dependence of the wave function. And we know how to deal with time dependence of the wave function. We use the time-dependent Schrodinger equation. So if our wave function, if we're not in a stationary state, but we're in some linear superposition of multiple states, then the wave function will evolve with time, and it should evolve according to the time-dependent Schrodinger equation, which is written here. So we have our h naught that we had before, and now we have the time derivative term. We still have the potential on the right-hand side. And then here I've also shown an extra term, which is just a relativistic correction to this non-relativistic time-dependent Schrodinger equation. In practice, this might be small depending on what pion mass you're looking at. And so we can just solve the time-dependent Schrodinger equation, which should take into account the fact that we have still some contamination from excited states. And finally, we can also look at the ratio of the two-nucleon correlation function with the square of the single-nucleon correlation function, as we did when we were talking about extracting energies from the Lucier formalism, to just isolate the part that cares about the interactions and also to increase the precision. And so, okay, so this is great. We don't have to go all the way out in time. We can account for the additional time dependence of excited states. And so we don't have to deal with the signal to noise issue at very, very large times. However, there's a caveat. You do have to evolve in time. So how much do you have to evolve? So when I say that we can account for all of the time dependence from excited states in terms of time evolution of the wave function, I'm assuming that all of the different states see the same potential. So all of the states that contribute must see the same potential. So when is that true? That's true as long as your two nucleons are always in their respective ground states. So if I have two nucleons that are scattering with the lowest momentum mode in my box versus two nucleons scattering with, say, 1 unit of relative momentum inside the box, those nucleons will see the same potential. Just because they have different momenta doesn't change their interactions. However, if one or both of the nucleons has an inelastic excited state, so it's excited to some resonance above the single nucleon, then that will see a different interaction with the other nucleon, and therefore we would not have the same potential. So the requirement here is not that we go out far enough in Euclidean time that we have a single state contributing. However, we do have to go far enough out in Euclidean time that inelastic excited state contributions have vanished. And this needs to be checked by looking for time dependence of the potential. So this is where the real benefit lies for the potential method. We don't need single state saturation as we do with Lucier. We only need elastic state saturation. But this does need to be confirmed with the data. Another benefit is that we get nearly continuous phase shifts. So with Lucier, we put our system in a box, we get a set of discrete energy levels, and those correspond to a set of discrete points along the phase shift plot. With the potential method, though, we have the wave function as a function of all possible positions on the lattice. And each of those positions corresponds to a different momentum on this phase shift plot. And so these are nearly continuous. The distance between points is set only by the lattice spacing. Some cons of the potential method. Well, so for Lucier, we didn't have to do a volume extrapolation because we use the finite volume to our benefit. We only required that the volume was big compared to the size of the interaction. So no infinite volume extrapolation needs to be performed. With the potential, however, we don't use the finite volume to our advantage. We do need to perform an infinite volume extrapolation, or at least look for any volume dependence of our potential as a systematic. And then finally, perhaps the biggest con of the potential method is that we've introduced this uncontrolled expansion. And so convergence needs to be verified. So, okay, I will go ahead and pause the video here.